This is the video supplement to the guided project work for the course CS571 AI-based robotics at the University of Washington. In this project, we tackle the problem of state estimation from images, that is, given n number of images and corresponding delta state as label. Can we use a neural network to predict the delta states for the next time step? We started off by generating appropriate data sets to train our neural network. Using the cardboard simulation from assignment 1, we generated 220 epochs of data, where each epoch consisted of 50 images and corresponding delta state as the labels. Using the data loader function in PyTorch, we developed an iterator class which created the trainx and trainy for the CNN. The data is therefore a rank 5 tensor, which is accompanied by a torch tensor consisting of 4 delta states. Using this data, we trained 4 different types of neural network, details to be discussed later. Here's the quick overview of our CNN architecture. We start off with a batch of small n images that is passed through the CNN. We experiment with the different values of n in our project. A 3D column of size 3 then slides through the images, generating a feature map. Since there are k-such kernels, we get key feature maps. Each of these is fed through a rectified linear activation function followed by a max pooling, which reduces the dimension of the image. We should know that only one convolution step has been shown in the figure in our work. But in our work, we experiment with the value of capital N, that is the number of the conv 3D layers. The feature maps after the max pooling is summed along the image axis and is then flattened out. This flattened image is then fed through the fully connected neural network of that M. The prediction is therefore received at the output layer, which has the information about the 4 delta states.
So we trained a total of 4 neural networks. We started with the lightest version and then built a heavier version of that neural network, which had more number of convolutional layers as well as fully connected layers. And then we used the same heavier network but took in less number of images as its input to see how many number of images are optimal for predicting the delta sets. All of these neural networks had a batch size of 128. They used mean squared error loss function and use Adam as the optimizer and ReLU as the activation function. So looking at the output, we will see the comparison of predictions from all of these neural networks at a later state, but right now we can see that at the bottom the error curve looks to be fluctuating a lot for less number of iterations. So for less number of iterations, it seems like the neural network is not learning, but if we train for large enough number of iterations, we see that the overall trend is decreasing, as we can see on the bottom right, which plots the average mean squared error per 100th iteration. So then we trained a heavier version of that neural network, which had more number of convolutional as well as fully connected layers, which also had a similar decreasing error trend. And then we also trained a neural network with 4 images as an input instead of 5, and then 3 images as input instead of 5. As we can see from the comparison of their predictions, as expected, we see that the neural networks which are heavier tend to perform better, and the neural networks that take in more number of images tend to perform better than the one that take less number of images. One more thing to note here is that even though the theoretical minimum limit for the number of images to predict delta states is 3 for predicting second derivatives, we see that for card3net, which takes in 3 images as an input, it performs kind of okay for the first derivative, but it doesn't perform as well for predicting second derivatives, which are ddx and dd theta.
While working on our project, we realized several limitations to our neural networks. First, we cannot make predictions at the beginning of an epoch or at the end because our neural network requires a sequence of before and after images. Second, due to how the test data is structured, our neural network cannot make predictions on its previous predictions, unlike in Gaussian processes. This is because we also take in an after image as our input. Third, we see our network performing poorly when the cart pole is at a standstill. As can be seen in the graph, the acceleration oscillates a lot, but our network does not capture this well. This is either because a sequence of standstill images do not provide enough information, or because the network sees less training data for the swing up policy. Finally, we see that more images provide better predictions, especially in the second derivative graphs. Through this project, we gained first-hand experience on deep learning. We learned about the intricacies of how to create a dataset and transform it into data to feed into the neural networks. And we also learned about the different hyperparameter choices we can make for the networks as well. Finally, we would also like to thank the course staff and the online forums, as well as several other resources we use to figure out our project.